All right. I just want to add a little bit to the cobwebbing diagram of last time, just to show you that in this case, the equilibrium is actually just stable from both the left and the right. So let's suppose that I actually started out with a very high dose of Tylenol. Maybe it was like 3,000 milligrams or something like that. Like, I'm really pushing limits here. But I know that, okay, I did this because I was in a lot of pain, I was ambitious, and after that, every single 6 hours, I'm only going to take 1,000. So in other words, the only thing I'm changing is my initial condition, but I still have the same updating function. So in the next 6 hour chunk, I go through a half-life cycle, and I take 1,000 milligrams. In other words, this updating function graph still applies. I'm just changing my initial condition. So I'm somewhere around like 3. Okay, so now, cobwebbing. Cobwebbing is an algorithm that really only has 2 steps, which you just repeat over and over and over. So the first step is you travel vertically to your updating function. Okay, and vertical does not mean upwards. Vertical means up or down. It's just a vertical travel. And then your second step, once you've hit your updating function, is you want to travel horizontally to the equilibrium line, to the y equals x line. And horizontal does not mean right, it doesn't mean left, it means right or left. Whichever way you have to travel to get to the equilibrium line, that's the way you do it. Okay, then you repeat this. Repeat. Okay, so let's do it. All right, and I should have given myself a reference. Let's see, I'm kind of in between these 2 dots, so let's just go on up in between these 2 dots here. There we go. Boop. All right, so I traveled vertically. Oh, to the wrong line. That red line is the line y equals x. Right? So I was supposed to travel vertically to the black line. All right, here we go. Bing. All right, there we go. I've made it to my updating function. Travel vertically, step 1. Now I travel horizontally to the line y equals x. So I guess that means left in this case. Right? And in the last case, that meant right. I went up and then I went right. So this is why I say horizontal. Right? Left or right. Okay, now I have to travel vertically to the updating function. Oh, and in this case, that means I go down. All right, totally fine. So I'm going this way. Then I travel horizontally to the equilibrium line. Then vertically. Then horizontally. And so on and so on and so on. And so you can see I am marching towards equilibrium. So here's your cobwebbing algorithm. And in this case, we can see that the equilibrium of having 2,000 milligrams in our system is stable. Okay, which means we travel towards it, whether we begin with a dosage that was higher than 2 or a dosage that was less than 2. And I do mean 2,000 milligrams. All right. Let's look at some more stuff. So let's stay with this theme of, I guess I went to Tylenol, but before that was bacteria, so that's what we had in our mind. Okay, so let's say we had a bacterial infection. Okay. And maybe the amount of this bad bacteria, maybe it's like a strep throat or something like that. Well, let's say I sample it at exactly whatever its doubling time is, okay? Whatever that unit is, maybe it's every hour. Don't know, don't care. But, so the amount of bacteria is going to double. But then, my body's fighting this infection, so I'm also going to kill off some amount, okay? And so gamma is just going to be the maximum amount of bacteria that my body can kill off per hour. That's just, okay, I'm on full alert here. So this is I just completely made this up. Right? And you might have a lot of ideas about how to improve this model, and that's fair. That's great. Be a scientist. Think about how we can better model what's going on. Something that we don't really talk about in this course, but there's no reason that gamma shouldn't also depend on time, right? Maybe it takes some time for my body to ramp up an immune response. And then I start to just really get going. So maybe this gamma used to be smaller, then it grows and grows and grows. But since we're only interested in dealing with one variable in this course, gamma is just going to be a constant. All right. So the question that I want to look at, now that we have the toolkit of cobwebbing, is how does the initial bacterial population that I'm exposed to affect the long-term dynamics? Okay? So if we graph a function like this, all right, then what does it look like? So I'm going to graph the updating function. Graphing the updating function means my vertical axis is b sub t plus 1. My horizontal axis is b sub t. And the equation that I want to graph is output is equal to 2 times the input minus gamma. Okay, so I should probably get down into the negatives. And then I want a slope of 2. Okay, so maybe it's something like this and this, here, 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 here. Okay, and so I can take this point all the way on down here and let it snap over. Great. All right, here's my updating function in black. Let's do the equilibrium line in red. All right, so I can graph that. Here's my equilibrium line. This is my population at time t, continues to be the same into the next time. Okay, so let's look at this question. How does the initial bacterial population affect the long-term dynamics? What the heck does that mean? First off, there's some equilibrium state where the amount of bacteria that I kill off kind of equals the amount of new bacteria that's generated. And let's go ahead and find that really quick. So before we start to answer this question, let's add another question. Let's find equilibrium. Okay, so what does that mean? So it means I need to find this point of intersection. This point of intersection occurs when both this equation is true and this equation is true. And essentially what we do is we equate the sides that involve the b sub t. Okay. Now, your instructor will probably show you a different method, which is equivalence, and the textbook has a different method. The way the textbook does it, the textbook says, all right, here's my updating function. My function of b sub t is equal to that. All right. And what the textbook tells you to do is just solve b star equals f of b star. What does that mean? It means they want you to solve b star equals 2b star minus gamma. So this is what the textbook would say. What I say is, hey, we're trying to find the intersection of two graphs. That means both of these equations are true, equation 1 and equation 2. And so if I was trying to find the intersection of two lines, then essentially, like if one of my lines was y equals 2x minus gamma, and my other line was y equals x, to find the intersection point, that means I have to equate these two things. And in this case, with the variable names I've chosen, that means I have to equate 2b sub t minus gamma with b sub t. All right, but notice we have the same equation. We just named our variables differently. All right, so let's do it. So if we want to solve this, let's go ahead and subtract b sub t from both sides. And while we're at it, let's go ahead and add gamma to both sides. So when I add gamma, that gets rid of that. When I subtract b sub t, that gets rid of that. And I'm left with b sub t on the left is equal to gamma on the right. Okay, so this spot here is gamma. So if the bacterial population was dead on equal to the amount that I'm able to kill off every hour, then it would just stay the same because they're able to double every hour. I'm able to kill off exactly that amount every hour, and it's just this constant battle. All right? Okay, now what if my initial population was somewhere over here to the left? So here's B0, my initial bacterial exposure. I shake someone's hand, and then I touch some food I'm about to eat, and I'm exposed to some bacteria, but it's not too much. All right, so I cobweb. So I travel up until I hit my updating function. Then I travel horizontally to the line y equals x. Did my pin just die? My pin just died. All right, let's finish this video without a pin. And that's okay. So I travel horizontally to the line y equals x. Then I travel vertically. But notice the vertical travel that I want to do to my updating function. I just want to get dotted lines. It's going into the negatives. And I cannot have a negative bacterial population. So if I am to the left of this equilibrium point, my body wins. I actually kill off the bacteria. Let's see this happen in a little bit more dramatic of a fashion. Okay, let's just move where I start. So I'm going to start just a little bit to the left. All right, so what happens? I come up here, I go here, 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 and now I've killed them all off. It took, let's see, 1 generation, 2 generation, 3 generations, and by the 4th generation, after 4 hours, I've won the battle. The dirty food that I ate, I've killed off all the bacteria, and I am not sick. Okay, however, let's see what happens if I begin just a little bit to the right of gamma. Okay. Oh, and I should say, since we traveled away from equilibrium, this is unstable on the left. Okay, so a value to the left of gamma, I was unstable. All right, here we go. So now I'm a little bit to the right. I go up. There we go. Then I go over. And then I go up. I go over. I go up. And I go over. And hopefully you can see what's happening. That bacteria is winning the battle. Right? Here, my starting value is here. Here's the 1st generation, 2nd generation, 3rd generation, 4th generation. These bacteria are just growing and growing and growing, and I am getting sick. Okay? So, how does the initial population affect the long-term dynamics? Well, if I'm above equilibrium, the bacteria win. I can't kill off enough. But notice in either case, I'm traveling away from equilibrium. So this is also unstable on the right. Okay? And since it's unstable on both sides, we just call this unstable. This equilibrium point here is unstable. Okay? All right. So that's kind of nice. Maybe I don't start feeling sick unless the bacteria are above some threshold, right? So if the bacteria up here, I'm feeling pretty sick. But if the bacteria down here, I'm not feeling too sick. So if I wanted to kill off more bacteria, maybe I go and I see a doctor and they prescribe antibiotics. And then what those antibiotics do is they're going to beef up this gamma, all right? They're going to let me kill off much more bacteria. They're probably also going to decrease this number here. They're going to make it much harder for bacteria to reproduce. But, all right, we're going to make this capital gamma, right? Now I'm fighting with medication. So what happens now? Well, I still have a very similar picture, right? All I've done is change my y-intercept, okay? So in fact, we could just use our imagination and pretend that this black line is actually just a graph of the new thing, the 2b sub t minus capital gamma, okay? But the point that I want to make is if you start taking antibiotics, and for whatever reason, so I was trying to come up with this on the spot, and there's some subtle issues, but nonetheless, hopefully I can still make this point. If you start taking some antibiotics, and for whatever reason, it makes your bacterial population start dropping, Okay. You know, it's dropping, it's going down. Or I could say it's here and it's going down. And then you manage to get into the range where you don't feel sick anymore. Okay? Suddenly you're in this zone here where you're not feeling sick. Maybe you have this much bacteria. So you stop taking antibiotics. But then those antibiotics are gone. So we no longer have this capital gamma, right? That's gone. We're back to lowercase gamma. Only our body is fighting off the infection now. So once you stop taking antibiotics, you're back to this dynamical system that's already pictured. And maybe you stopped when you were here, because this is in the level where you're not feeling sick. But, you know, a couple more generations of this go by, and that bacteria starts creeping up again, and you start feeling sick again. And this is why they tell you to complete the full round of antibiotics, because they want the bacteria level to drop to a point where they know you're going to win the battle. Okay. All right, so what did we do in this video? We cobwebbed again. We did a quick recap on how to find equilibrium. Here we saw an example of an unstable equilibrium. And since the pin's dead, we'll call that good for this one.